The screen is visible, right? Okay. So if anybody is not able to see the screen, please let me know. So we have come to week 7 of this course on Python programming, data structures, and algorithms. So this week 7 and week 8, in my opinion, are the most interesting because we'll see some advanced stuff in these 2 weeks. So this week we have seen abstract data types, classes and objects in Python, user-defined lists. We have seen how lists can be defined by the user using a class. And we have seen how search trees can be defined by the user using a Python class. So these two classes are here. So this is the class corresponding to a search tree. And this is the class corresponding to uh, a list. That is a linked list, basically. Okay. Okay. All right. So now we are going to look at some questions related to this week. So this is the first question. So I'll let you read the question for a minute and then we will discuss.
Good evening, sir.
Good evening. So we are discussing the first question of this week. So you can try to solve the question, then we will discuss. So is there anybody who has understood the question? If you have understood the question, please write yes. So please also explain us about generating the previous permutation of sequence as well. Yeah, we can do that. In fact, when we will discuss how to generate the next permutation, then it will be quite obvious how to do the previous permutation. So I'll give you a minute. You can think about it. So try to generate. So maybe try to uh, think of an algorithm that will work to find the next permutation of the sequence. So anybody has any answers?
30 seconds, sir.
Okay, take your time. Okay, there is an answer from Gahan. FJAD. Yeah, this looks correct. Okay, so there is an answer from Monish. So the answer from Gahan and Monish differs slightly. Yeah, it differs not slightly in multiple places. It differs. Okay, so I'll show you the answer. So here is the answer. All right, so we'll discuss how to get the answer. But yeah, so I think Monish is correct. Let me check. Let me verify. So FJAD CBEGHI. Yeah. So Monish, would you like to give uh, some explanation why you answered this? I mean, how you got the answer? Would you like to say a few words about how you got the answer?
Yes, sir. Sir, is my voice audible, sir?
Yes, yes. Please go ahead.
Sir, actually, I followed a three-step algorithm in finding the answer, sir. So the first step is that I identified the first decreasing position from the right side of the sequence.
Okay.
And next, so after I got the first decreasing position in my sequence from the right side, so next I swapped it with the next largest letter of that first decreasing position's letter, sir. Then the position after the first decreasing position's letter, so I will get a suffix. So I reverse the suffix. So after reversing the suffix, the final sequence which I will get is FJ, ADC, BE,
All right, fine. This is correct only, but I will explain the steps, although this answer is correct. So let's understand how somebody can find the next permutation in the dictionary order. So I will copy this sequence. Let's go to the whiteboard. So this is our sequence. All right, so this is a sequence. And what are we interested in? So we're interested in finding the next permutation in dictionary order. Okay. So, I mean, yeah, that is our goal. Okay, so what shall we do? Like, so can you tell me, uh, so let me ask you a concrete question. So, does there exist a permutation of these letters? These letters means these letters. These letters. Does there exist a permutation of? I just copy this. For which there is no next. I mean, larger. Larger means next, right? We are going in the dictionary order. So, what is the dictionary order? The alphabetical order. Okay. So, A is before B, that order. So, does there exist a permutation of this string for which there is no larger or next permutation? That is the question I'm asking.
So if there is no large one, then you have to go to the smallest one.
No, so if there is no larger means there is a permutation for which there is no larger permutation. That is the largest. So the answer to this question is either yes or no. So do you go for yes or no? So what is the permutation of these letters? So it's some ordering of these letters. Okay. So how many permutations of this string are possible? How many letters are there in this string? 5, 6, 7, 8, 9, 10. So there are 10 letters in this string. So how many permutations of this string are possible? 10 factorial. That is true. So there are 10 factorial permutations only. So out of them, one must be largest, isn't it? So there should exist a permutation which is the largest. So what is that permutation? So the answer to this question is yes. Then my next question is, this is question number 1. So what is the next question? That what is this largest permutation?
The descending order, basically.
The descending order. Yes. Yes, the descending alphabetical order. See, yeah, so if it is ordered in the descending order, that means you start with the largest letter. So in this case, I mean, yeah, so with letters it's slightly difficult, but yeah, so you understand that the descending order permutation is the largest. Beyond that, there is nothing. Okay, so this observation is going to help us uh, design an algorithm for finding the next permutation. Similarly, this algorithm is also going to, this observation is also going to help us in finding an algorithm for the previous permutation. Okay, so let's start with, this is a 10 letter string. This is slightly complicated, but we'll start with a toy problem. Okay, I think that is easier. So let us, this is for warm up only. Let's not worry about it too much. This is our question. This observation, I'll keep it to the side. Now we'll start with a toy problem. So now I am saying that let us start with uh, some numbers. So I'm asking that, so let's say the string is not this. So what is the next permutation? I'll just say permute for permutation of, I let us say 1 3 4 2. So I'm starting with a smaller example. I'm saying that you have a string which is one. You can think of it as string. You can also think of it as a number. But let's say it's a string 1 3 4 2. Then what is the next permutation? That means what is the larger number where you are using 1 3 4 and 2? You have to design a 4-digit number just larger than this.
One, 1423.
1423.
Yes, 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 yes. So the answer is okay. 1 4 3. Yeah. So now, okay. So how quickly you found this answer? Yeah. So now you think that how, what happened? I mean, what did you actually do? What are the steps you actually followed to get the answer? Give it a thought for a minute, then we will proceed forward. Four three two one is not the next one. 4321 is the largest. So 4321, somebody has answered 4321. So 4321 is the largest number you can get using 432 and 1 without repeating digits, of course. Means there's nothing larger than this with these 4 digits without repetition. And let us try. Okay, I will give you some hints. So let us look at it. So I'll just do it this way. So 1 4, oh sorry, 1 3 4 2 is my number. I'll make it large. So what you know that 4321 is the largest permutation. That is the largest number. So in the 4321, that number, everything is in decreasing order. So if numbers are in decreasing order, so if all the pairs, consecutive pairs, so let me write 4321 as well. So 4321 is the largest number. So what happens in 4321? If you look at pairs, the pairs are sort of in decreasing order. So 4 3 is in decreasing order, 3 2 is in decreasing order, 2 1 is in decreasing. So in fact, if you take anything and like 4 and 1, if you take, so any two numbers digits you take, they are in decreasing order because overall number is in decreasing order of the digits. So what are we going to do? That we are going to scan this permutation from right to left and see if the decreasing order property is maintained or not. Okay, at whichever point the decreasing order property is not maintained, we know that there is a possibility of making a swap and get the larger number. Okay, so I will just write down what I said. So my first step will be this. Uh, Let me write it properly. There is some message. No. So I'm going to find the an ascending pair. So if it is descending order, then it is fine. So I'm going to find an ascending order. First is scan from the left. So why is it not typing? Yeah, scan from the right to look for uh, an ascending pair. That is my first step. So what I'm going to do, 2 4, that is the first pair. I mean, so 4 2 is the first pair. They are in descending sequence. They're in descending order. It's not a problem. So I go to the next pair, 3 4. They're in ascending order. So we have identified the rightmost ascending pair in this permutation. So 3 comma 4. So I'll just so I'll write it. So I'll say that identify I'll just say identify the rightmost ascending pair. So in this case, what is the rightmost ascending pair? In this case, it is 3 4. Yeah. Okay, that is the first step. Why I am doing that? Because if it was already in descending order, then I don't have a way to move forward to the next permutation. Okay. So what is the second step? So this is exactly what Monish has said, but I'm trying to explain the logic behind it also. So now I have identified this pair 3 4, and then I'm going to look for the smallest number to the right of 3, which is larger than 3. I'm going to say that identify the smallest number greater than 3. 3 because 3 is where the issue of descendingness, ascendingness has happened. So 3 4 is the pair we have identified. 3 is the first element of the pair. So I'm going to identify the smallest number which is greater than 3 to the right of 3. Why I'm going to identify this number? Because I want to bring that number in the place of 3 and I want to send 3 in the place of that number so that I can get as small a number as possible. But I want this to be larger than, just a second. Let me verify if I'm saying the correct thing. Yeah, so I found the first decreasing pair 3 comma 4. Then I'm going to find the smallest number which is greater than 3. Yes, to the right of 3. This is correct. So what is the, so I'm looking at 3. So what is the smallest number greater than 3 to the right of 3? So here there is only one number which is greater than 3, which is 4. To the right of 3 there is only one larger number, but there could have been more larger numbers, right? So I am going to identify the smallest number but greater than 3 to the right of 3. But here there is only one number which is greater than 3. That is 4. So in our case, this is 4. So I bring, okay. So I bring this larger number 4 in the place of 3 and I send 3 to the place of 4. So now I'm going to swap these two numbers. It's my next step. So now after swapping this step, swapping 3 and 4, my permutation is 1, 4 has come next to 1 and 3 has gone next to 4. This. Okay. Yeah. So I think Monish said something else. Is this all we have, or we have to make changes, Monish? Yes, who was talking? Who has given the right answer? Onish only, I think. So after this, we have another step. This is like we reverse the uh, suffix. We reverse the suffix after 4. So 4, of course, uh, 4 is what we need to make things larger, but we reverse the suffix after 4, because if we don't reverse, then we do not get this the smaller numbers. So after this, our permutation becomes 1 4 2 3. So now my claim is that 1 4 2 3 is the largest number after 1 3 4 2. So what is the next largest number after 1 3 4 2? My claim is it is 1 4 2 3, which is you have answered. Okay, so this is the algorithm. So any questions on the algorithm, like anything that doesn't look right? You give it a thought for some time. How to find the previous permutation? I will come to that. First, try to digest what has happened, that how we found the next permutation. So if you understand what has happened, apply the same algorithm on this string and then find the answer. Okay, so you have found the answer. Anybody else? Apply the same algorithm. So identify the rightmost ascending pair in this string, and then you identify the smallest uh, character to the right of your left element of the pair, which is larger than that number or that character. Then you swap these two things and then just reverse the suffix to the right of the pair. Okay, I'll do it. So I'll write here only, and we'll see if I get the right answer. We have to take the ascending order in step 4. Reverse. We have to. So Gahan is saying that we have to take the ascending order step 4. Try to. So you're saying that instead of reversing the suffix, you want to just take the ascending order of the elements next to. Correct. Let's run this algorithm on this string and then we will see. So we'll identify the rightmost ascending pair. So look at the rightmost pair, EC. Is this ascending or descending? This is descending. E is larger than C. So E is the fifth letter, C is the third letter. So EC is descending. There is no problem. G comma E, again descending pair. There is no problem. H comma G. GH. So H comma G is again descending pair. There is no problem. I comma H, HI. So that is again descending pair. There is no problem. The problem arrives here. So BI is in ascending order. B is smaller than I. So we have identified the rightmost ascending pair. So I'm going to write it here. So this is the other case. So I'm going to, yeah, maybe I'll just say comma. I use red. Okay, sorry, not red. Yeah, maybe I'll write in square braces. So BI is the pair that we have identified. Okay, which is in ascending order and rightmost. So identify the smallest character greater than. So instead of 3, I'll say greater than B, which is to the right of B. So to the right of B, what all things we have? We have these things. Out of these things, what is the smallest character? I, H, G, E, and C. So C is the smallest character. So C is the smallest character. I have identified it. Maybe I'll remove these things. So now I'm going to swap these two characters. Okay. So I swap these two characters. Now what do we get? So I'm going to swap B with C. Then I get this thing. So remember our pair was this. So I reverse the suffix after 4. So after 4. So 4 is means after I. Then what will it look like? No, after 4, it is after 4. I should say after 3, right? Because see, we have already brought C here. So you have to revert. So wherever we have brought the next largest character, from there we have to revert. So you revert this part. So once we revert this part, what do we get? So I'm going to copy this. So C is already here. So this part we don't care. We only care about reverting this. So BEGHI. This is what I'm going to write in the reverse order. Yeah. So this is the final answer. So how this is the next permutation? So what did you have? You have this thing. So you identified that the smallest character that you can bring to get the next largest string is C. After you bring C, then you want to have something which is uh, uh, in ascending order. So that's why something that was already descending, you reverted it and you got an ascending order. So these two things are equivalent, as Gahan has pointed out. There is some other answer. Anyway, so yeah. So now that you have understood, before that, any questions on how to find the previous next permutation? After that, we will go to how to find the previous permutation. But if you understood this, then we'll just make one observation and we will use a similar algorithm to find the previous permutation. Any questions? Okay. So look at this observation. So when we are interested in finding the previous permutation, then we will ask a similar question. So if we are interested in finding the previous permutation, Then we'll ask a similar question. So what question shall we ask? So we'll ask that does there exist a permutation for which there is no previous permutation? So we'll ask similar question. So what we'll ask? So yeah, so does there exist a permutation for which there is no previous permutation? The answer is again yes. The smallest permutation is itself the first permutation. Previous to that, there is no other permutation. Okay. So you are going to check whether everything is in ascending order or not. Okay. So if everything is in ascending order, then you are already done. Then now you have to give it some more thought that how you will design these 4 steps. So you have to basically design 4 steps only, but this time you are asking that what is the previous permutation. So the observation you are going to make is that there is one permutation which is the smallest permutation before which there is no other permutation, and then you can design this algorithm. So if you have any other specific questions, then I can answer regarding how to find the previous permutation. Anything on the chat? So similar thing you have to do. So you have to find the rightmost character that is larger than its next character. Okay. So that means uh, wait. So you are checking for ascendingness, right? So if everything is in ascending order, then you are done. So you are looking for a pair which is descending. So if you find a descending pair, then you will observe that there is a chance of swap, and then you perform the swap accordingly, and then you again do a reversal of the suffix. So it's almost same, but I think this is in the yeah, I think this is in the assignment of this semester. Explain once again. So explain once again which part, the next permutation or the previous permutation? Saurabh, are you there, Saurabh? See, the
Previous
next
permutation.
previous. Okay, so the previous permutation part is the assignment, if I'm not wrong. And I think the assignment deadline is over.
No, sir, tomorrow.
Okay. So similar thing you can do. I will not give more details, but try to assimilate what has happened for the next permutation. So I'll repeat the next permutation again. So you know that there exists a permutation for which there is no next permutation. So what is that permutation? That is the largest permutation which is in the descending order. So anything in descending is good for you. So for example, 4,2 is all right for you. So you start scanning from the right, or maybe I'm looking here. Start scanning from the right. You look at the first pair. Is it descending? If it is descending, you go to the next pair and you keep going as long as you don't find an ascending pair. As soon as you find an ascending pair, you observe that there is an opportunity to generate the next permutation from here. So how do you do that? So you identify that what is the smallest larger character to the right of where this anomaly has happened. So that character and this character you swap, and the after doing the swap, the remaining characters you put them in ascending order. Okay, because you want to put them in ascending order because you're interested in the large or next permutation. If you're interested in the previous permutation, then obviously you will put them in the descending order and not ascending order. Okay, the similar thing you can try to do. I'll not give more details, but yeah, spend some time on this. This is not very trivial. Uh, okay, so that much I will say maybe.
This previous permutation, at least you can tell the steps what to be done.
I don't know if that is as per protocol, the assignments should not be discussed for which the deadline is not over. But I'll give you some clues maybe. Uh, but I cannot give you the full algorithm. But the clues maybe I have given you already, that you look at the permutation and you have to generate the previous permutation. So you do some scan. I will not tell right from right or left, but you identify a place or a pair where this uh, ascendingness is not there. There is a descending pair. You identify a descending pair, and you know that there is an opportunity to generate the previous permutation at that position. And then you identify which character is to be swapped with that character where uh, uh, the descendingness has happened. Okay, and then you do that swap, and then you reverse some part. So that much I will tell. Uh, you try with some numbers. Maybe you try with 14342, and you try to generate the previous number. Then it will be easier. Okay, so we'll go to the next question. So you have seen the linked list implementation using a class. So I hope you have watched the videos. So it is possible uh, to use class to implement linked list. Okay. So in this question, we are asking that, okay, so if, since you have seen this class node, or maybe I'll just show you the class node in case you have not seen the videos. So here is the class node. It has a constructor. So what does the constructor do? The constructor allows you to instantiate an object of the class. We have seen the object-oriented programming concept in this lecture. So you can generate or instantiate objects from a class, and to do so you have a function which is called the init function, which is also called constructor. And in the constructor you pass some parameter. Sometimes you don't pass anything, but it must take a copy of itself to be able to generate the object. So in this case, what is happening? To generate a node in the list, you are sending a value. You are sending a value to the constructor, and then it generates an object of the class node using these three lines. So in the first line, the value of the node is set to the value that you have sent via the parameter. In the second line, It is saying that the next node after this node is null, that it does not exist. So self dot next is none. That means you have seen linked list. So a linked list starts from its head and then it proceeds, and at the tail there is no next node. The next node is set to none, and then you return. That is a constructor initialization of this class. And there are certain methods within this class. For example, this method is to check whether the class is empty. So it is just checking whether the value at the node is none or not. If it is none, that means there is no value to start with. So that's why you are able to check whether the list is empty or not. So this is the implementation of append. So we have seen that in a list, in the inbuilt list, how we can append. We can say my list dot append something, and that thing gets appended to the list. So they have implemented this thing with the help of a class. So this function is for appending, so which we have seen previously. This function is for insertion. So there is a minor difference between append and insertion. And this is for deleting. So for deleting, what you will do, you have to tell which value you want to delete. So you're telling, you're passing the parameter that this is the value you want to delete. Is the previous permutation. So some people are, so I do not know what is the previous permutation. I have to calculate. But yeah, you can spend some time on it. Okay, so this is how we have seen how the class node is defined. Okay, so in this class, can we add a function len that implements user defined lists which will compute the length of a list? So in a list, how many elements are there that we want to compute using a function called length? Okay, an incomplete implementation of length is given below. You have to provide expressions to put in place these blank spaces like triple x, triple y, and triple z. Okay, so here is the question, here are the answers. I'll give you some time, you can give it a thought, then we will discuss.
Maybe option for itself.
I was not able to catch what you said. Option 4. Charan is saying option 4. Yeah, I mean, fine. Why is it option 4, Charan? Maybe a sentence.
Sir, for a subject value equal to none, means there is no value in the list. That means there is length is 0.
Mhm.
In
Yes,
a list, dot next equal to none. That means next value is empty. That means one value is only present in that. And we
yes,
also judged one. It calculates form data if next is not none. That calculates again in length.
correct, correct. Okay. So yeah, rest of you give it some thought. Option 3, Salmabi. Why is it option 3, Salmabi?
I think for ZZZ we are calling self dot next dot length. So for the last element we already getting the elif option, that is 1, y is 1 already we are getting. Then I think it will be add up like that.
Okay. Okay. Fine. So we want
So
to compute. Yeah, go ahead.
nothing says nothing.
Okay. So what do we want to do? We want to find the length of the list. Okay. So I'll just copy this. So we want to compute the length of a list. That is our goal. So I'll just try to conceptually see what is happening. So our goal is to compute the length of a list, and this is a function that we are defining. So this is a function. All right. So let us see a list. So let us say first value in the list is 12. So how we had implemented list? You remember how we had implemented list? So we had a situation like this. Maybe we had a list like this: 4 plus followed by 6, followed by 9, followed by 12. So the length of the list is 4. So now the way they have implemented the list, you look at the implementation. So they have for every node they have a value, self dot value, and there is a next pointer which is initially set to none. But once you append new things, for example, look at this append. So you're appending a node with value v. So first it checks that whether the list is empty or not. If it is empty, then you make a note. If it is not empty, then you say that self dot uh, if it is, sorry, what is this? If self dot next is equal to none, that means self dot next is equal to, there is only one node. Then you make a new node. You call the constructor and make a new node, and you point the current node to the new node. So the new node is pointing to null, and the current node points to the new node. And if the list already has more than one elements, then what you do is you recursively call append on self dot next. Okay. So what it means is that we will be able to insert only at the end of the list, because only at the end of the list self dot next will be none. Okay. So to look at it visually, we have a situation like this. So as per the implementation, we have like boxes. Like this is the first box for the first node. Then there is the next node. Then there is the next node. Then there is the next node. And after that, there is no other node. And there are, so to say, pointers. So here to here, there is a pointer. Here to here, there is a pointer. Here to here, there is a pointer. But here to here, just a second. Here to here, there is no node to point to. That's why I'm saying that here there is none. Okay. And you know the values already. So this is 4. This is 4. This is 6. This is 9. And this is 12. Okay. So this is the implementation as per the class. So every node has two components, the value and the next pointer. Okay. The last element in the list is pointing to none. So that is the implementation. So now we want to compute that what is so what is self? This is the beginning. The beginning is self, right? Let me check once again. So when you append, you go to self dot append and you okay. Uh, okay. So every node has a self copy. So every node has a copy. That is fine. So now we are going to check that to count that there are 4 nodes in this list. What should be the values here? So if somebody gives this list to this function, then first thing it checks whether the list is empty or not. If the list is empty, that is self dot value is none. So this value, if it is okay, so this is the self node. This is the first thing. So this is, so to say, the beginning of the list. So let me call it self. So if this first node is itself pointing to its value is none, then there is nothing in the list. It's an empty list. So it should return 0. So triple x is 0, and that is clear. But if the self dot value is non-zero, but self dot next is none, that means there is no other node except the first node, then the length of the list is 1. Okay. So what happens when the value at the first node is non-zero, non-none, and the next node is also non-none? That means the list size is at least 2. Then what you would do? And then we look at the options. So we have a tie between these two things. So triple Z is either self dot next dot length, or it is self dot next dot length plus 1. Okay, so let me copy this. So what does this contain? Self dot next means this node. When self is this, so self dot next is this, right? Oops. So this is self dot next. So whatever is the length, if you start counting from self dot next, whatever that length is, the length of the list is one more than this length, isn't it? So this part, why is it? So this part of the list is is corresponding to self dot next. I mean, if you look for self dot next is this node, and the length of self dot next. So the self dot next dot length in this case is 3. That means if you start counting from this node, so there are 3 nodes, but the entire list has size 4. So therefore, here we should write 1 plus self. 1 is corresponding to the self node plus the remaining part of the list, length of that, self plus next dot length. So I'll just copy this. Yeah, so this would be Z. So is this clear why 1 is required? Because 1 is for the first node, self node, and the remaining things we are recursively calling length on the remaining list.
Yes, sir. Yes, sir. Understood.
Anybody else who thinks that option 3 is correct? Option 3 means without the plus 1. So what is option 3? It's option 3. So at this point we can take a break, and we will come back in some time. In fact, we have 2 more questions. These 2 questions are not too difficult. Yeah, so we will discuss question number 3. So what I'll do is I'll copy this function and put it in the chat box. Then I will show the definition of the class tree. So this is the function that we are looking at. and the function is called foo. And what is the question? What is it? What is it computing? All right. So okay, there's already an answer. Uh, okay, so there's already an answer, but yeah, I mean, you give it a thought. I will show the definition of. I'll also write the question in the chat box. I'm also putting the question. What would and now I'll show you the definition of my tree. I mean, that's tree class. This is the definition. So you have to worry about the constructor. So at this point, we will take a break. With 7:09 p.m., we can come back. At 7:20 p.m., we can be back. Okay. We can come back at 7:20. All right. Okay, so we'll start again. So there are a number of options people have chosen. Uh, Salma is saying 4, Arun Ram is saying 3. Monish is saying the number of leaves in my tree, which is option number 4. Uh, Gahan has said option A. Arun Ram has said option 3. There is length of the longest path from. Okay, so a lot of people have said a lot of things, but let's look at this from a conceptual point of view. Yeah, I hope I am audible. Is there anybody who is not able to hear me? All right. So try to look at it conceptually. So you have seen the definition of the class tree. So the tree has, uh, I'll just look at it once again. Look at the constructor. It takes a value and it initializes self dot value to that initial value. And to the left of that node, it generates an empty node. To the right of that node also it generates a node. So left child is empty, right child it is also empty. When you create a new node, the new node is formed with that value, and left child and right child are empty nodes. Okay, that's what happens if the self value is none. Means if you start with an empty tree, uh, otherwise also means whenever a new node is formed, this new node has both its left and right children empty nodes, right? So now let's look at the question again. So you have a tree. In this tree, uh, you are first checking whether the tree is empty or not. If the tree is empty, then you return 0. Then you are checking that if the tree itself is a single leaf. So is leaf function we have defined. If you see, is empty is also there and is leaf is also there. I think, for example, is leaf is empty is there. Oh, this is not tree. Tree is this one. Insert, find, copyright, make empty. Is empty is there. Is leaf is also there. So uh, if you encounter if you give this function a leaf node, that means both its children are empty, then it will say yes, it's a leaf. It will return true. Otherwise, it will return false. So both these functions are already in the class. Now you are using these two functions within the new function, that is foo. So if this leaf is only this tree is only a leaf, or if you encounter a leaf, then you return 1. Otherwise, you recursively call this function foo on the left subtree and on the right subtree. Okay. Okay. So, right. So many people are saying option D now. So why is it option D, the number of leaves in my tree? Let us look at a picture. If it returns 1 when a leaf is found, yes, that is true. That is basically the point. Should I draw a picture? Okay, let me draw a picture. A small picture might help. It will take few minutes, but it will be helpful. So let us draw a picture. So yeah. So let us say here is a tree. So this is my tree. Okay, I will draw the edges. So in this tree there are two leaves. So I am going to call this function foo on this root node A. So here is my function. I will copy this. Copy. We'll quickly copy this function. Yeah, so the indentation has been disturbed. Okay, don't worry. Okay, that's the problem actually. Let's not. The indentation should be correct, otherwise it's difficult. Yeah, now it's fine. So you send the root node. So at the root node, it is neither empty, the tree is neither empty nor it's a single leaf. So there's a recursive call at B and C. Again, it is not a leaf. A leaf should have both none. So this is also necessary. So this is none. This is none. This both things are none. And this both things are none. Okay. So leaf means both the children are none. So there are two leaves in this tree, as you can see, F and E. So, so initially foo is invoked on A, then recursively it is invoked on B and then on C, B and C. So B is not a leaf nor it is empty, so it invokes it on D. C is neither empty nor it is a leaf node, it invokes it on F. At F, at F, the function will return 1 because it's a leaf node. This part, this elif part will be executed, its leaf. So in F it returns 1. So whatever it returns, that gets added to the left subtree. Left subtree is nothing. So this gives 1. It goes here, goes here. So at A, from the right subtree, only one leaf node is reported. So similarly at E also, we get one leaf. So it returns 1. And D also gets 1 because E gives one leaf from the so D's left subtree reports one leaf, D's right subtree reports no leaves. So B's right subtree together reports only one leaf, left subtree is reporting no leaves. So B overall reports one leaf. So A gets one leaf from the left subtree and one leaf from the right subtree. If return one, well, yeah, fine. That was previous message. So overall A will get two leaves. So that is why it is easy to see that this function is going to return the number of leaves in the tree. Any questions? It's very important to see this sentence uh, to see why this is not computing the number of nodes in the tree. So if you add just 1 plus this thing in this line, then you would be in fact counting the uh, number of nodes in the tree. All right, so shall we move forward?
Yes.
So this is the last question of the day. Oh, sorry, yeah. So you have seen both pre-order and in-order traversal, I think. Is there anybody who hasn't seen uh, in-order traversal and pre-order traversal? Okay. So I'll explain the question. So we have a binary tree with 10 nodes, and the 10 nodes are labeled A through J. And we also know that the pre-order traversal is given by this string, and the in-order traversal is given by this string. So from these two information, uh, is it possible to uniquely identify the tree? Let me go to the whiteboard. There is a pre-order and in-order traversal. So I'm asking the following question. So I'm asking that from the above information, is it possible to uniquely identify the underlying tree? I mean, can there be two trees for which the pre-order traversal is this as well as the in-order traversal is this? That is the question. So its answer is either yes or no. This is the question I am asking, but they are asking a different question. They are asking that what is the right child of the root node? That is our question, but I am asking a different question. This is a different question, which is our goal, which we'll take care later. But before that, we want to answer this question.
Yes.
Yes. Okay. Saurav B says J. I don't know what J means, but Khan says yes. Okay. All right. Okay, then try to answer this question. Okay, so let me define for those who don't know what is in order and pre-order. I will define pre-order and in order as well. In fact, it is written in the question. So what is pre-order traversal? You start with the root, you print the root, then you print the left subtree in pre-order, that is recursively. Then you print the right subtree in pre-order, that is a pre-order traversal. In order traversal we have already seen. You print the left subtree in order, then you print the root, then you print the right subtree in order, that is in order traversal. So in order is left followed by root followed by right, and pre-order is root followed by left followed by right. Okay, so Saurav is saying that the right child of the root node G is J. Okay, small j, that makes sense. Okay, so there's an answer already. So in order, what does it mean? It means left followed by, I'll just say, maybe I'll just say comma, root right? And pre-order means root, left, right. We'll take an example. In fact, we can take the same tree, right? We can take the same tree. Okay, yeah, it's going to take some time. I'll just give you some more time maybe. What is the root?
G is the root.
Okay. Why is G the root?
In pre-order, root comes first.
Yes. So from the pre-order sequence, the first letter is G. That means G must be the root. So it is clear that the root is G. It's clear. It's not a problem. So any progress? So this is our question. So G is the root. That is clear because G is the first letter in the pre-order traversal. So let us try to identify that. Okay, G is the root. Then what are the letters or what are the nodes in the left subtree? What are the nodes? Oops, I want to draw an ellipse. Maybe I'll draw this thing. So this is a left subtree, this is a right subtree. Is it possible to sort of move things around? Okay, so there is a left subtree. Is right. So first I want to identify that what are the nodes in the left subtree and what are the nodes in the right subtree. Specifically, since we're interested in the right child of the root node, what are the nodes in the right subtree? That is my question. Something more concrete, some intermediate step. So what are the nodes in the right subtree of G? Salma is saying JAFT. Why JAFT?
In order traversal, from the right side of the root are the right leaf members. So
Yes,
after
yes, yes.
G is JFD.
Yes. We have to observe that in the in-order traversal, G is here. So that means whatever is to the right of G is definitely in the right subtree of G, because in order, what is the traversal order? Left followed by root followed by right. So everything that is in the left subtree of root will come first, then the root will come, that is G will come, and then the right subtree will come. So whatever is to the right of G, that is JFD, JFD, these four letters or nodes are in the right subtree. So what are the nodes in the right subtree is definitely JFD. That is clear. So in the right subtree, what we have, so I'll delete the right subtree and I will just write JFD is to the right. J, A, F and D in some order. We do not know what is the parent-child relationship, but J and FD are in the right subtree, and our answer that what is the right child of the root is one of these four things. So the remaining things are ruled out. Okay. What shall we do now? Krishna is saying D is the right child of root G. Why is that?
Because in the pre-order traverse, the root comes first.
Yes,
So
so G is our root.
D comes in that JAFD sequence.
Yes, so yes. So
So it
observe
should be
that.
the root.
Yes, yes, yes. So in the pre-order traversal, if we look at the remaining letters, the remaining nodes, so G is definitely to the root. You see that these four letters J, F, D, what is their ordering here? D, A, J, F. So D is the first appearance. I mean, out of J, A, F, D, the letter that appears first in the pre-order traversal is D. That means D must have been the root, or rather, these other things, AJF, would they cannot be the root of D. So D is the root of these all other things. I mean, D is ancestor of AJF. So D must be the right child of G. So it is clear from this pre-order traversal, since D is appearing before all these other guys, so D must be the ancestor of all these guys, A, J, F, and since D is the ancestor, we can write D here. So we know for a fact that D is here. So the remaining things are there in some order. So D is removed from here. So there is an edge between G and D. The remaining things are also there. In fact, we can complete that full tree. So any doubts on why D is the right child of the root node? Okay, now I will complete the right side of the tree. Left side you can complete. So now what we will do? So look at J and J, A, J and F. So say A is coming before J and F. So A would be either to the left of D. So A could be the left child. So what can happen is it is possible that A is here. I'm just saying that it is possible, but it could have been the right child also. So if it is the left child, then we have to place J and F in some way. So I'm just guessing now. It is probably not true. You have to also correlate with the in order traversal. So J and F, say J is coming before F. So it may be possible that J is here. And F is here. Maybe possible. It's a guess. Okay. So now whether this is true or not, you have to check the in order traversal. So in the in order traversal, we have left followed by root followed by right. So this is the root. We don't worry about the left subtree. Left subtree is already is not our concern at all to decide what is the ordering or what is the parent-child relationship in the right subtree. That is independent. So say JAFT. So now if I do if I do an in-order traversal, so what is the in-order traversal? ADFJ. So there is a problem. So I have to make it JAFT. So how to do that? How do I make it JAFT?
In the in order traverse, since
Yes.
there is no children to the right of D, right child
Yes.
not be there. I
Yes.
think.
Right side. That is true. So J, oops, this will work. So see, if you do the in-order traversal in the right subtree of the root, then you have J, A, F, this is the left part, D. And then of course you have G. So this is the right subtree. Similarly, you can design what is the parent-child relationship in the left subtree. But you understand how to do it. So the right child of the root node is D. And the question could be slightly more difficult. So one might ask that what is the right child of D? There is no right child in this case. One might ask what is the left child of D? Then you have to do it accordingly by, processing these two traversals. Yes, go ahead, Saurabh. You have a question? You raised your hand. Any questions on this question? So next Monday we'll meet. But for the regarding the extra session, see, so far whatever we have discussed in this 7 weeks have been very structured. We have seen what are the assignments of previous offering, and we have solved these assignments. Next week we are going to solve the assignments for dynamic programming. It will be very nice, and it's quite interesting in this course to see dynamic programming in Python. But we can have a session where things could be open-ended and we need not follow a protocol that we have to solve assignment questions only. But there is almost no time. So when is the exam date?
22, sir.
So one option is we can meet next Monday, that is 17th. There is a question. Monish is saying, please, can you elucidate on how to practice solving search trees problems? I mean, are you looking for some sample questions? So you have to solve some sample questions. And the best way to find the questions is from the internet, I think. So one option for the extra session is we meet on this Monday and discuss week 8. All right. So once we discuss week 8, then we are already on 17th. So 18th, next day, immediately on next Tuesday, we can have the extra session. So Monday followed by Tuesday. Next week, both Monday and Tuesday, we can have sessions, if that is fine with you. That is the only option I see. There is no other option, because by 18th, all the extra sessions should be over. That is the instruction from NPTEL. Beyond 18th, one cannot hold any other sessions, because the exam is on 22nd, as you were saying. So does it sound good to you?
Fine, sir.
Okay. Okay, so at this point, we have come to the end of this session for today. I thank you for attending. If there are any questions, then you can ask me. Otherwise, this is officially the end of the session.
Sir, what is the class? There is definition separately, and what how it is different from a definition. Class is different from a definition.
So class is an abstraction. So if you have seen the videos, then you will see that in the 7th, initially itself, the professor is discussing about some abstract data types. So class is an abstraction. Okay. So for example, uh, we are abstracting the tree as a class. We're saying everything can be thought of as a class. Uh, and classes, the instantiation of classes are called objects. Okay. And it helps in two respects in object-oriented programming. One is called abstraction. So think of abstraction this way. Suppose you're driving a car. So you're driving a car. You know how to drive the car. You know what to do with the steering wheel. You know what to do with the brakes. You know what to do with the clutches. You know what to do with the accelerator. But you don't need to know how these components are working internally, how the engine is getting ignited, how the pressure on the shoes are, how the brakes are working to bring the car to a halt. All these things internally, how these are happening, what is the engineering inside, that you need not know. So there is an abstraction between you and the intricacies within the engineering of the car. So you are only bothered about what are the tools that you have to use. So similarly, the class is an abstraction for the programmer, uh, that lets you make use of certain functions which are uh, your interfaces to interact with the class. You need not worry about how the functions are defined. For example, if you look at this class, then this tree class we have seen. So suppose somebody has written this class for you. You know that this class is written uh, uh, to abstract a tree. So you need not worry about how isEmpty is implemented. What is the definition of isEmpty? What is the definition of isLeaf? What is the definition of find? These things you need not know. As long as you know that what is the what to say. This is called what is it called? Forgot. So how many parameters the function is taking? So this is called the signature of the function. As long as you know the signature of the function, you can use that function. So basically, the intricacies within the functions are abstracted away from the user. So in large programs, what happens? sometimes you don't need to know about so many details of so many things, then you ask somebody to write some classes for you, and you just tell him that what are the operations you want to perform. Then the person tells you that, look, I have created a class for you, and these are the operations you can perform on the class. Then you only worry about how to use the operations without worrying about what's inside the class.
Okay.
So one thing it achieves is abstraction, and there's one more thing it achieves. So you can instantiate objects. So there is so two objects. For example, you can make a class uh, human. From there, you can make two classes, male and female. So the male also derives some properties from human. The female also derives some properties from the human. And but then there are certain properties which are distinct to the male, certain properties which are distinct to the female. So repetition can be avoided. Uh, that is one thing. Other things are also there. For example, uh, I mean, I think he discusses it. So if you take any object-oriented programming book, you will see what are the benefits and advantages of using a class inside a program.
What is object-oriented programming?
So object-oriented programming is when you make use of classes. So classes are, as I said, it abstracts out information from uh, so certain information which are not necessary for the programmer are hidden from the programmer. So so when you make use of classes and objects, then that paradigm of writing programs is called object-oriented programming. That you are using objects for your purposes. That is your style of writing program is using classes. So you Google it. What is object-oriented programming? So more details will be found.
Okay, sir. Thank you.
Yeah, so these kind of questions we can discuss more freely. You can ask me these kind of questions which are not directly related to the assignments, and we can talk freely in the extra session. You can clear your doubts regarding anything on Python. You will be free to ask me anything regarding Python. We'll try to discuss next Tuesday. Anything else?
No.
So Gahan is asking a question. How n factorial approximates n by e to the power n? Yeah, so there is a derivation for that, that y in factorial is almost like n by e to the power n. It takes some time and effort to derive that. So maybe this is a good question we can discuss on Tuesday, Gahan. Anything else? If you have algorithms related questions, then also you can ask me. So next week we'll see nice. So this dynamic programming is a paradigm of algorithm design. This is a very well studied topic in algorithms. So I think it will be nice to know some DP techniques next week. So I will encourage you to watch all these videos. The eighth week is really nice, and you know it's quite stimulating. Okay, so if there are no other questions, then we can conclude the session. I will stop recording.